Just a little bit on vector equations of lines first of all. So we start at the origin and then we get onto the line. And this vector here, the position vector, is what gets us onto the line. So if we just look at L1 for a second, then this would be 1, 10, minus 3. Then the direction vector is what tells us how the direction that we then go along the line. So this, for example, and lambda is what we multiply by. So if I want to go to here, it'll just be twice as much as if I go to the first point. So this is going to be lambda times 2 minus 5, 4. And what I'm getting at really is if we want to show that two lines are perpendicular, it's actually all about the direction vectors. So L1 and L2 are perpendicular if the direction vectors are perpendicular. We can take the dot product. 2 minus 5, 4 dotted with 1, 2, 2 is going to equal 2 times 1 plus minus 5 times 2 plus 4 times 2. And this equals 0. And because the dot product, the alternative way to do it is to say that it's the magnitudes A, B, cos theta, then these are non-zero, so it must be that cos theta is equal to 0, which means that theta must be 90 degrees. And actually, it's just enough really to say if the dot product is 0 to say they're perpendicular. I've just shown a little bit extra. So therefore, L1 perpendicular to L2. Part B says to show that L1 and L2 are skew lines. That means that they do not intersect. So then we'll know they're perpendicular, but they don't intersect. And if you kind of put your arms out with one of them going, say, to the right and one of them going up, but a bit away from you, then that would be an example of two lines that are skew but perpendicular, because there will be a 90-degree angle between them. Okay, so to deal with this, what we can do is assume that they actually do intersect. Assume L1 and L2 intersect. Then at the point of intersection, the remember we've started at the origin and we're going to some points like here, and then we'd have, if they did intersect and you had some other line like that, then you get the same position vector on both lines, which means I can set the x components equal to one another, the y components equal to one another, and so on. So 1 plus 2 lambda will equal minus 1 plus mu at the point of intersection. Just taking the tops and set them equal. 10 minus 5 lambda equals 2 plus 2 mu. Minus 3 plus 4 lambda equals 3 plus 2 mu. And I'm trying to show that there's no solution to this. I'm going to label this one equation 1, this one equation 2, and this one equation 3. And then I'm actually going to take my third equation and minus my second equation, because this works out really nicely because I've got 2 mu in both of them. And I'm going to do it this way around because then I'm subtracting a negative and things stay positive. Although having said that, I'm going to get minus 13. Right, but then I'm doing 4 lambda minus minus 5 lambda. That's going to give me plus 9 lambda. And that is going to equal 1, which means that lambda, if I add 13 divided by 9, is going to be 14 over 9. I can then sub this back in, sub into either 2 or 3. I'll go with 3, I think. Then I would get minus 3 plus 14 times 4, that's going to be 2856 over 9. And then if I minus 3 again, that will equal 2 mu. Minus 3 minus 3. Actually, let's just put another line in. So that'd be minus 6, which I could then write as minus 54 over 9 plus 56 over 9 equal 2 mu. That will give me 2 over 9, so mu will equal 1 over 9. And now I just need to check that it also works with equation 1. Check, because I've not used that so far. So 2 and 3 are consistent. There will be there is a solution that satisfies these two. Right, now the left-hand side of 1 equals 1 plus 28 over 9. This is 9 over 9, so it's going to be 37 over 9. Whereas the right-hand side is going to equal minus 1 plus 1 over 9. That's minus 9, I'm going to get minus 8 over 9. So they are not equal, and therefore the equations are inconsistent. There is no solution. So no point of intersection. And to conclude, L1 and L2 are skew. Now, the way I did that is absolutely fine. There is a slightly quicker way to do it, but, well, fair play if you managed to spot it. We could take equation 1 and times it by 2, which would then give 2 plus 4 lambda equals minus 2 plus 2 lambda. The thing about this is if you then combine it with the third equation, minus 3 plus 4 lambda equals 3 plus 2 lambda. So you've got the same coefficients now on lambda and mu. So if we subtract them, then we get 5 equals minus 5. And this is clearly a contradiction. And from that, we could straight away say that there's not going to be a solution and therefore they're skew. So it's just an alternative if you're interested, or maybe you did it that way, in which case, well done. Part C says that the point A with position vector given lies on L2. So I'm going to get a diagram down for this. I honestly strongly recommend diagrams, even though these are 3D vectors, we can still represent them on this 2D plane. So here's L2. Going to put the origin here, and then I've got my position vector O to A, which we're given as minus 1, 2, 3. I quite like to write it in column format. And remember again, we're potentially getting onto the line here and then going along to A. Okay, that's not vital at the moment, but I just wanted to get that on there. And then the point X lies on L1. So I'll draw L1 over here. And X can be here. We're then told one other piece of information, that's AX, so if I draw that in, is perpendicular to L1, so a right angle here. We're asked to find the position vector of X. So remember, I've got my direction vector for L1. It was 2 minus 5, 4. So if I take the dot product with AX, then I can work out, I should be able to work out the position vector. Okay, so let's write down AX. It's going to be AO or minus OA plus OX. And OX is, remember, this is just a point on L1, so I'm going to have some value of lambda with 1 plus 2 lambda and so on. So I can say that it is 1 plus 2 lambda, then it's 10 minus 5 lambda minus 3 plus 4 lambda. Actually, that's the OX part, and then I'm minusing OA, which, as I pointed out here, is minus 1, 2, 3. That's what we're given there. So that is going to equal 2 plus 2 lambda, then 8 minus 5 lambda, and minus 6 plus 4 lambda. So carrying on at the top, I can now say, this is still part C, that this vector 2 plus 2 lambda, 8 minus 5 lambda, minus 6 plus 4 lambda. Again, if I take the dot product, remember AX is perpendicular to L1, so if I take the dot product with the position vector, then I'm going to get 0. Since AX perpendicular to L1. All right, let's expand this out then. We're going to get 4 plus 4 lambda minus 40 plus 25 lambda minus 24 plus 16 lambda, and that's going to equal 0. I can bring these together, so that will give me 45 lambda, and then I've got minus 64 plus 4, that's going to be minus 60, is equal to 0. So 45 lambda is going to equal 60. Lambda is going to be 60 over 45, which is 4 over 3. Okay, so I'm nearly there. So now I want the position vector of x. So I want OX, and I can put it back into here, 4 over 3. So this gives, so OX, I'm going to get 1 plus 8 over 3, which becomes 11 over 3. 10 minus 5 times 4 over 3. Okay, I've done this already now, so I'm not going to go through every calculation. 10 over 3, and then 7 over 3. What then I did is I decided to take the factor of a third out and write it as 11. Third times 11, 10, 7. For D, AX, we're simply minusing this from it. And if you follow through the calculation on that, keeping the third outside, then it becomes a third times 14, 4, and minus 2. Which means if we want to find the magnitude, then we can apply Pythagoras. So we can find the length of this vector and just then times by a third. Okay, so we don't need to do anything with that third really. You can square it and then square root it, but there's no real need. So a third times the square root of 14 squared plus 4 squared plus minus 2 squared, same as 2 squared. 14 squared is 196, plus 16 plus 4. So I get square root of 216. Now I'm dividing by 3, so actually that's the same as dividing by the square root of 9. And 9's into 216 are actually 24. So the final answer is root 24. I think the answers accept some non-simplified versions as well. And we could even simplify the third, to be fair, but I think writing root 24 is pretty good. Nice. That takes us to the very last parts of this question. We're told that the point B, distinct from A, also lies on L2, and the distance from B to X is the same as the distance from A to X. Now don't forget we worked that out previously, it's root 24. Find the position vector of B, so that's going to be OB. Well, we have information on BX, so let's focus on that. BX is going to equal OX minus OB. And OX is something we calculated earlier. It's a third, 11, 10, 7. And then for OB, because it's a point on line L2, I can use this equation here. And I just need to work out what mu is. So I'm going to minus 1 plus mu, 2 plus 2 mu, 3 plus 2 mu. I'll keep the factor of a third outside. So it'll be a third, 11, 10, 7. Do you know what? I'm just going to put an intermediate step in, minus a third, and times everything through by 3. Minus 3 plus 3 mu, 6 plus 6 mu, 9 plus 6 mu. Then bring it all together, it's going to be 11 plus 3 minus 3 mu, because I've got this negative here. 10 minus 6 mu, 7 minus 9 minus 6 mu. Gives a third, 14 minus 3 mu, 4 minus 6 mu, minus 2 minus 6 mu. And remember, I know that bx squared is going to equal 24. Okay. So let's apply Pythagoras. It's going to be a third squared, and then 14 squared, sorry, 14 minus 3 mu, I should say, squared, plus 4 minus 6 mu squared, plus minus 2 minus 6 mu. Do you know what? We can just say 2 plus 6 mu, because there's two negatives. It doesn't matter about the... If you square minus 3, it's the same as squaring 3. So let's just square the negative, which is 2 plus 6 mu. That's going to be 1 over 9. Right, let's do this. 196 plus 9 mu squared minus 14 times 3 is 42. So I'm going to get 84 mu plus 16 plus 36 mu squared minus 24 twice, and minus 48 mu. then plus 4 plus 36 mu squared plus 12 mu plus 12 mu, so 24 mu. And remember that is equal to 24. So let me times through by 9. 180 plus 36 gives 216, so 216. Is it a good idea actually to do that? I think I'm going to leave it like it is for the moment, as 1 over 9. Okay, so I'm going to add up all my mu squareds. That gives me 7281 mu squared. Then these, the minus 48 plus 24 gives me minus 24, so I'm going to get minus 108 mu. And then 196 plus 4, that's 200. That's quite nice. 216. Okay, and actually this is good because rather than timesing through by 9, I can actually divide each of these terms by 9. 9 mu squared minus 12 mu plus 24 is equal to 24. So these two cancel, leaving me 0. And therefore, I can divide through by 3. 3 mu squared minus 4 mu is equal to 0. Factorize out the mu. 3 mu minus 4 is equal to 0. So mu is equal to 0 or 4 over 3. I'm going to put both values back into our value of bx, which was this. Okay, sorry, didn't quite copy it across. So mu equals 0 is going to give 14 over 3. Actually, I just might as well keep the third on the outside. The third times 14 4 minus 2. Actually, this, if you look back in the question, is ax. So it's not, I don't need to like reject that solution as such. Well, I will reject it as b, but it does equate to a solution. It's just that it's ax. And then mu equal to 4 over 3 is going to give bx. So if you substitute in 4 over 3, then you actually get a third 10 minus 4 minus 10. This is bx. In fact, we weren't asked for that. We're asked for OB, the position vector. And for that, you don't need bx because you can just substitute mu back into this one. Minus 1 plus mu, 2 plus 2 mu, and 3 plus 2 mu. And that ends up being a third times 1, 14, 17. Again, I'm not going to do all the calculations, but it's just involves fractions and everything, and hopefully it will work out for you. Finally, we're asked to find the cosine of angle AXB, this one here. So we can now apply the dot product of, actually it's going to be XA with xb. And we've got ax, so we just need to switch the signs around to make it minus ax. And this becomes, I'm now going to bring, no, I'll leave the, no, I'll put the third inside, I think. So minus 14 over 3 minus 4 over 3 and 2 over 3. And I'm going to dot that with xb, and I just worked out bx a minute ago. So this ends up being minus 10 over 3, 4 over 3, and 10 over 3. And don't forget that this is also equal to the magnitudes, with which we know they're both root 24, times by cos of this angle. So we just need to work out the dot product parts by timesing across, and better just make a bit more space for that. So 140, 14 times 10 over 9, minus 16 over 9 plus 20 over 9 equals 24 times our cos of our angle. This comes together to be 144 over 9. And 9's into 144, it will divide into it, will be 16. So 16 over 24 equals cos of our angle. And finally, cos of axb, if we're simplifying it, is equal to 2/3. Okay, I thought the start of that question was quite nice. You know, just showing lines are perpendicular and skew. That's not too bad. Position vector of x was, yeah, a bit more involved, but it's like not unseen. And then D was okay as well. I thought the last part was pretty tough. There is a way that the mark scheme does it, involving a dot product with a unit vector and things, and I've got to be honest, I don't quite understand it. I have looked over it. Um, they use the midpoint. I think that's a bit of maths I haven't quite familiarized myself with, so I'll be more than happy to hear a good explanation of that, because the mark scheme is quite brief. Ultimately, I think I'm pretty happy with my method by, again, writing down bx in terms of mu and finding the length. I've done this on other AEA papers, and it's not always the quickest route, but it gets me there. And also, you can be quite confident about it, since we managed to get 0, which gives ax, and then the other solution, seems to make sense. And then right at the end, and one final dot product. Well done.